So in the previous video, we talked about how the exact nature of the amino acid can be different depending on the pH of the solution that it's in. All right. Whenever you have very low pHs, that's when you're going to have the amine would be exist as the ammonium form. When at very high pHs, your carboxylic acid is going to exist as the carboxylate. But in the intermediate forms, you're going to have it exist where you actually have one negative and one positive charge on the molecule, and the name for that is a zwitterion. All right, in order to be a zwitterion, you have to have an overall neutral charge. All right, it has to be a molecule that has at least one positive and one negative charge somewhere on it. All right, so a completely neutral molecule but without charges is not a zwitterion because you need to have some charges somewhere. All right, so this brings us to the concept of an isoelectric point. All right, so if you have an amino acid, all right, we can see here that there's a certain pH where there would be an overall -1 charge on the entire molecule. There's another pH where there's an overall +1 charge on the entire molecule, but there's also a pH in between where you have this zwitterion where it would be electrically neutral. All right, so this is going to be true of all free amino acids, is that there is a pH where it is going to have an overall 0 charge or an overall neutral charge. All right, so you might think that, okay, well, if this is the way amino acids work, that isoelectric point is always going to be around a pH of 6. All right, and for a lot of them, it is around 6. All right, so if you go through the isoelectric points, and this is pointed out, this is what this number is in the right column of the data booklet. You can see that the most common isoelectric point is around 6. All right, and that's the reason for that is because for most amino acids, what makes the isoelectric point is this situation right here. All right, but when you're looking through these isoelectric points, you'll notice that some of them are pretty far away from 6. All right, for example, lysine is 9.7. We have glutamic acid, which is 3.2. And so the question is, how is it that you can have an isoelectric point that far away from 6 when it looks like that's the pH that would give you this neutral condition? All right, and the reason that you can have isoelectric points that are far away from that, I guess middle pH, has to do with the nature of the R group. All right, so remember that with your amino acids, you not only have your amine here, your carboxylic acid here, but you've also got this R group right here. And if this R group happens to be something that doesn't have any acid, weak acid, or weak base type functional groups, like a carboxylic acid or an amine, for example, if it was just a hydrogen here like glycine, or if it's just a methyl group here like alanine, then yes, you will have your isoelectric point right there around 6. But if it's something that's got something else, then you can have isoelectric points that are very far away from 6. All right, so to give an example of that, well, first of all, I'm going to point out lysine has got the 9.7, aspartic acid has got the isoelectric point of 2.8. We're going to consider aspartic acid. So if we look at the structure of aspartic acid, it looks like this. All right, so there's your normal carboxylic acid, there's your normal amine, but you'll notice that part of its R group includes this second carboxylic acid right here. So remember what we said about carboxylic acids. They tend to have a pKa of somewhere around 2.2. So that if you are above that 2.2, it's going to exist in this form. If you're below it, it's going to exist as the HA form. All right, so let's consider what would happen if we had aspartic acid. All right, so if it's sitting in a solution whose pH is 1, all right, both of these carboxylic acids are going to be in their HA form, all right, or another way of saying in their acid form, but this the amine is going to exist in its ammonium form. All right, so on the other end of things, at the highest pHs, both of your carboxylic acids are going to be in their carboxylate form, and your amine is going to exist in its A minus form. All right, and again, there's no minus charge on there. It's just relative to this right here. This has got one less charge. All right, and if you apply it to a pH of about 6, you would have this existing as the HA form. Your carboxylic acids would exist as their A minus form. All right, so this would be the predominant thing that you would have, the way that this molecule would exist if the pH of the solution was 6.0. All right, so if we can count up the charges for each of these different molecules, this would have a +1 charge. This would have a -1 charge because you've got 2 -1s and 1 +1. And this would have a -2 charge. All right, so here's the thing. How do we know that the isoelectric point is not 6.0 or around 6? Because at a pH of 6, this molecule, the predominant thing that exists, does not have a neutral charge. All right, so if at 1 the charge is +1 and at 6 it's -1, what that tells us is that somewhere between these two pHs there's going to exist a situation where the molecule is going to have an overall 0 charge. All right, and so if we drop the pH a little bit from this point right here, chances are there's going to be a point where one of these carboxylates goes from being in its A minus form to being in its HA form. All right, remember when the pH is right around the pKa, all right, is right at the pKa, you have a 50-50 percentage of the HA form versus the A minus form. All right, so, and again, these carboxylates are going to have very similar pKa's. So another situation you might have would be if this one right here is in its HA form and this is in its A minus form. All right, so this is going to be at a very narrow pH range. But if you look, figure out what is the charge on these molecules right here, well, each of them would be exactly neutral. All right, so these are both what you would consider zwitterions because it has at least one positive and one negative, but overall the charge is 0. All right, so the question is what, the isoelectric point is going to be the pH where these guys are the predominant things that exist. All right, and that happens at a pH of 2.8. All right, so if you look at aspartic acid and you look at its isoelectric point, the reason that is the pH at which this thing is overall neutral is that's the pH where it's going to exist like this. So next thing we're going to talk about is how could you separate free amino acids. All right, so first of all, how would you end up having a mixture of amino acids? Well, if you had a protein and you've got a long chain of amino acids, all right, and you wanted to figure out what amino acids were in that protein, one thing that you could do is treat that protein with an enzyme called, I believe it's, okay, you could treat the protein with pepsin, which is the enzyme in your stomach that breaks down proteins into the individual free amino acids. All right, so once you had your free amino acids after you break down the protein, you want to figure out what amino acids are in that mixture. All right, so one way that you can separate different amino acids is what's called paper chromatography. All right, this is very similar to a technique in chemistry called TLC, which is thin layer chromatography. But essentially what you have here is a strip of paper. All right, a lot of times this strip of paper would be, it's almost like coffee filter type paper. All right, it's very absorbent. And what you do is you cut it into a little strip. This would be about the size, maybe about the size of a microscope slide, and you dab your mixture of a solution containing your proteins onto the paper right there. You don't need a lot. Okay, it's going to be weigh like a couple milligrams worth of material right there. All right, and so then what you do is you put this in a container where you dip the bottom end into a solvent. All right, so what's going to happen here? So paper is made of cellulose. All right, and cellulose is a material. It's a polar material that has has some water molecules that are actually trapped between the cellulose fibers. All right. So when you attach, put a little sample of your protein mixture onto this, the more polar the amino acid is, the more it's going to want to stick to those water molecules, because water is a very polar molecule. All right. So what's going to end up happening is we're going to put this down into a solvent. All right. And a lot of times this might be a mixture of alcohol and water, for example. And what's going to happen is the water is going to start to soak into the paper. All right. If you've ever taken a paper towel and dipped it into water, you can see how the water kind of rises up the level, rises up through the paper. So it's that water is going to soak up, and it's going to rise up this piece of paper through something called capillary action. All right. So when that happens, the amino acids that are in this mixture right here are going to have a choice to either stay put exactly where they were dabbed onto that paper, or they can travel up the length of this paper. All right. All right. And here's an example of paper chromatography. So you can see here you've got a little piece of paper here, and it's sitting in this container. And the solvent, you can see where it's risen to. There's the line right here where below it it's kind of wet, but above it it's somewhat dry. And originally these things were spotted right down here. And as that solvent rises up, it's going to carry some of the material with it. All right. And so here you can actually see through a couple different colors. There's an orange here, a brown here, and a blue here. And that's because the original mixture contained a couple of different compounds. And as it rises up, the things that like to stick to the water molecules don't travel as fast as the things that aren't quite as sticky as to the water molecules that are embedded in these cellulose fibers. All right. And what that allows to happen is that your compounds can start to separate. All right. Okay. So when you're done, all right, you're just going to take your paper out of the solvent, and you're going to be left with your spots in different locations. All right. Sometimes you actually have a couple of different amino acids that might have the exact same spot. All right, or it might be in the same location. And one thing that you can do there is you dry off your paper, and then you turn it sideways and let the solvent run up in the other direction. So if I take this strip and I turn it sideways, what is now up would actually be in the direction that would be sideways here. All right, there's actually a picture of that in your chemistry, the review manual for this. I'll show that to you in class. So one thing about this is there's a way to designate where your compound is with this measure called RF, which stands for retention factor. All right, and the way the retention factor works is if this is where you originally spotted your material, and this is where the material ends up, if you measure that distance right there, all right, that would be your X. And then if you measure the distance from this, so this is the level that the solvent eventually rose to. All right, if you measure the distance from there to there, from there to the original place of the origin, that would be your Y distance. That ratio is what's called your retention factor. And the reason that they use an RF to designate this instead of just a plain distance is the farther you let the solvent go up the piece of paper, the farther your spot's going to travel. But what's always going to be the same is that the ratio between how far your spot traveled versus how far the solvent front traveled will always be a constant fraction. All right, and that's why they use that to measure it. So the one thing that you can tell based on how far things traveled is that the less things travel, these were the things that really like to stick to the water molecules, and therefore they didn't travel that far. All right, the things that travel farther are things that weren't really that sticky with the water molecules in the original location, and therefore they were happier to travel farther, to travel with the solvent as it rose up the piece of paper. All right, so the lower things tend to be the more polar amino acids. The higher things tend to be the less polar amino acids.